Hi Mary Pat, welcome to what I'm thinking is day 4 of alkane naming. It might be day 3, it might be day 12, I can't remember. But whatever, we're just going to pick up where we left off yesterday. And remember that yesterday you were given numbers 9 and 10 as homework, whatever yesterday is in the universe in which you are watching this. Remember on numbers 9 and 10, I said for now we're going to go ahead and cross off these two extra groups on number 9. Okay, and then we're going to go ahead and name it from there. Remember, the very first thing we do when we're naming it is we find the longest chain. So how can we find the longest chain on this? You should have gotten something that looks a little bit like this. Remember this, there'll be a carbon at the end here. And then we're going to say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is the longest chain you could get. And so that's going to be a decane molecule. So decane will be the main part of this molecule. And then we have to talk about the functional groups. Okay, so we've got, if we number our carbons, in this case, it doesn't matter which way you start. So I'm just going to go ahead and start here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You could have started the other way and it wouldn't matter. Either way, you would still end up with the same small, the number difference wouldn't matter. Okay, so now let's name our functional groups. What do we have? We have a methyl at number 2. So we have 2-methyl. We have a methyl at number 4. So 4-methyl. Sorry, something weird happened. We have a methyl at number 5. 5-methyl. We have at number 6 an ethyl group because we have 2 carbons. 1 carbon, 2 carbons. So that's 6-ethyl. There we go. Number 7, we have another ethyl. So 7-ethyl. And at number 9, we have another methyl. 9-methyl. So that's what you should have gotten. You could have gone the other way, and then you would have gotten, if you number your carbons backwards, you would have gotten 2-methyl, 4-ethyl, 5-ethyl, 6-methyl, 7-methyl, 8, 9-methyl decane. Now, one thing to remember is that chemists are lazy, and so one thing I haven't taught you that yet, because I wanted you to practice naming first, was that there's a way to make this even easier. So if you'll notice, we have several methyl groups, right? We have this methyl group, that methyl group, that methyl group, that methyl group. So what chemists do, instead of naming them 4 different times, they combine them. So they say 2, 4, 5, 9 methyl, which means there's a methyl at carbons 2, 4, 5, and 9. True. And then they say, okay, cool, what do I have as far as my ethyls? I'm going to go ahead and wonder if I can, nope, I can't grab that. Okay, stop doing the thing. Okay, sorry, I'm just trying to move this decade. I'm going to have to just erase it. I need to give myself some more room. There we go. It doesn't want to do it. Okay, fine. Okay, anyway, so 2, 4, 5, 9 methyl. Now we need to name these ethyl groups, and I'm not going to have a lot of room to do this. It should go here, but I don't have room, so I'm going to write it down here. So it's going to be 6, 7 ethyl. So the proper name of this group, or this molecule, is 2, 4, 5, 9 methyl, 6, 7 ethyl decane. And remember, that's assuming that we cross off those 2 extra groups, which we're going to keep going with, and we're just going to keep it that way, okay? So again, the proper name of this molecule is 2, 4, 5, 9 methyl, 6, 7 ethyl decane. But what you should have gotten in your homework was this version, because that's all we've talked about so far. But I'm kind of adding a little bit to it for you. Now, this should be the final name of this molecule. Everything makes sense, and it's a nice, easy, efficient way to name it. Let me move this way. This 2, 4, 5, 9 methyl, 6, 7 ethyl decane. because chemists, again, want to do the most efficient thing possible. But for some reason, they add a little bit. And what they do is they say, instead of just saying, hey, I have a methyl at 2, 4, 5, 9, and an ethyl at 6 and 7, because of some weird cross-linking stuff that can happen in proteins later and blah, blah, not important for this class, but they go ahead and they add in the Greek prefixes for numbers. Okay, so what do you mean, Megan? What I mean is, if you have 2, 4, 5, and 9 methyl, you're not saying you have this methyl bound. One way you could interpret this, if you're being kind of stubborn about this, is that that methyl group binds everything together so that it's bound to the 2, the 4, the 5, and the 9, all bound to one methyl group. Now, that's not even possible, but, you know, just to make sure that people know, no, it's not one methane that's bonded to all these things, it's 4 methanes that are bound to all these things. We actually add one more wrinkle, and so we say it's actually 2, 4, 5, it's supposed to be a comma there, 9 tetramethyl. That means, remember when we did our naming of covalent bonding, tetra means 4. So we have a methyl group. There are 4 methyl groups, okay? There is one each, 4 methyls. There's one each at 2, 4, 5, and 9. So we need to add this right there. Okay, we're not done. We also have 6 and 7 ethyl. Again, there's an ethyl group at each point. So it's 6, 7 diethyl. And then again, decane. Decane. And that is the actual appropriate name for this. For this assignment, we should go ahead and start practicing this. So again, you have to figure out how long your chain is. Rule number 1, find out how long your chain is. Rule number 2, figure out the naming of the carbons, the numbering of the carbons, so that it's the smallest number for the functional groups. Number 3, what are the functional groups? And then organize them, okay? You may actually see in some cases, depending on the chemist, you may see people do one more thing, and that is that when they're naming their functional groups, they put them in alphabetical order. So if this were to be absolutely accurate, we would say, ethyl comes before methyl. So really, this should be 6, 7 ethyl, and then, 2, 4, I forgot di. There we go. 6, 7 diethyl, 2, 4, 5, 9 tetramethyl. Tetramethyl. Okay, running out of room. That's cool. All right. Tetramethyl decane. So this is the IUPAC accepted name for this molecule. It's long and crazy. That's okay. We go with it. It does tell us everything we need to know about this molecule. So now let's look at number 10. Again, we need to find our longest group. Hopefully this is becoming pretty old hat, as they say. Let's try going this way. So we have carbon at the end. 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's one option. Let's see if we can get any more than 8 carbons. What if I start here? We have 1, 2, 3, 4, 5, 6, 7, 8. 8 is the longest, right? So 1, 2, 3, 4, 5, 6, 7, 8. Or 1, 2, 3, 4, 5, 6, 7, 8. Either one of those ways, you're going to get the same thing. So we'll just leave it like this because I've already drawn it. Okay. So, and you could have done it either way. You're going to end up getting the same thing. Okay. So our base of this is going to be octane. So octane is the base. It's the carbon. And then we have groups hanging off of it. So what groups do we have? Let's name our carbon first. So we're going to have to name it going this way. 1, 2, 3, 4, 5, 6, 7, 8. And by name, I mean number. You know, sure. And then where are our groups? So using the old method that I taught you where you name each and every one individually, you've got at carbon 2, you have a methyl. At carbon 3, you have a methyl. At carbon 4, you have an ethyl, because we've got 1, 2 carbons. At carbon 5, At carbon 5, you have a 1, 2, 3 carbon. That is a propyl. Okay, so 5 propyl. Oops, changed colors on you there. Let me go back real quick just to be consistent. So 5 propyl octane. Okay, do we have any other groups left over? No, those are all the groups we have. Excellent. So now let's put these in order. So this is the way I like to do this. You notice that I haven't smushed anything together yet. I haven't put these two methyls together. I haven't put them in alphabetical order. I haven't done any prefixes. First, I like to kind of take an inventory of what the functional groups are and where they are, or else I start losing numbers because that's just how my brain works. If your brain wants to do it a different way and just put everything in alphabetical order first, that's fine, as long as you end up with the same thing. Okay, so let's go ahead and look what our final product will be, the final name of this carbon molecule. So we need to put them in alphabetical order based on the functional groups. Okay, so we have methyl, we have ethyl, we have propyl. So the first thing is going to be 4-ethyl, comma, okay. Fantastic. Ethyl is checked off. I've already named it. Next are going to be the methyls. So 2, 3. There's 2 methyls, not 1 methyl cross-linked. So 2, 3 dimethyl. Dimethyl. Excellent. Comma. And that just leaves the propyl molecule. So 5 propyl. But that's not it. We have to name our chain. So finally, octane. Oops. So let me zoom out and we'll see the entire name. The proper name for this molecule is 4-ethyl 2,3-dimethyl 5-propyl octane. Now this probably isn't what you got for your homework because I didn't tell you about the alphabetizing yesterday and I didn't tell you about the combination of the same molecules, but you should have at least gotten the same names for the functional groups. What's an ethyl, what's a propyl, how do I number my carbon chains, and what the heck do these lines even mean? They represent a carbon bond. All right, so we're on this worksheet, drawing alkanes from their names. So we're going to draw both the structural formula and the line angle formula or the skeletal formula for the molecules. I've heard this referred to as structural models and line angle models or skeletal models. Either way is exactly the same. So while that can actually be interchangeable, the naming system is universal. It's named by the IUPAC, which you may have heard in other science classes, the IUPAC naming. It's the International Union of something French about naming chemistry. It basically names all the molecules possible, so you don't name, and they establish and maintain the rules for naming molecules, so you don't end up with two things with the exact same name that are actually doing two very different things because they're two different molecules. That would be, sort of awful. So we are going to use these naming systems that I've been teaching you to draw the molecules instead of vice versa, which is all we've been doing so far. So it's important to remember that carbon, can make 4 bonds. We're only dealing with single bonds right now, so this makes it a little bit easier. Carbon can bind to anything. So far, we're just bonding with carbons or hydrogens. So it could be bonded to a carbon. If it's on the end of the chain, it's then going to be bonded to 3 hydrogens, okay? It could be in the middle of the chain, in which case it's bonded to another carbon here. Okay, so then it's only bonded to 2 hydrogens. That's what this thing is talking about. Okay, if it has some other carbon functional group, then if we're focusing on this carbon, okay, it will then be bonded to another carbon over here. Then it'll only have 1 hydrogen. Okay, and even then we could go a step further and say, oh, maybe it's bonded to 2 methyls. It's a dimethyl carbon. And so then it's bonded to no hydrogens. Okay, and so that's what it's saying here. So the more bonds that carbon makes with other carbons or any other molecule, the less hydrogens that can bond to it. Okay, remember, hydrogens basically, and we're talking about organic chemistry at this level, are just space fillers. They're bond fillers because we have to make sure carbon has its 4 bonds filled. Okay, so let's go ahead and look at this first guy, 4-ethyl octane. So the way we do this is we start with that carbon skeleton. That's why I always had you measure the carbon skeleton first, count the carbons to get your longest chain. And so the very last word is going to be the carbon backbone, that carbon skeleton, and it is octane. So the structural formula is the one where you draw every single carbon. You write out all the carbons, okay? So octane means 8 with all single bonds. So you're going to have 8 carbons. 1, 2, 3, 4, 5, 6, 5, 1, 2, 3, 4, 5, 6, 7, 8. Excellent. And we're going to go ahead and name. It doesn't matter which way we name. You can do it starting on the right and going left, but, you know, for convention's sake, I'm going to go and I'm going to start over here. So 1, it's going to be carbon 1, carbon 2, 3, 4, 5, 6, 7, 8. And the reason why I'm naming it, not just leaving it like it is because we have this 4 ethyl group. So on carbon 4, I need to put in an ethyl. Okay, so coming right off of carbon, draw this better. It looks like a double bond. Coming right off of carbon here. And it doesn't matter if you draw it going up or down. It's totally your preference. Remember, these are three-dimensional objects that can turn in space. Okay, on carbon 4, we have an ethyl group. And remember, ethyl means 2 carbons. So there's a carbon and there's a carbon. Excellent. Fantastic, except if we're doing a structural model like this, we also have to include our hydrogens, okay? So this is a question of how many hydrogens does every carbon have? The ones on the ends, okay, remember they're making 4 bonds total. Every carbon has to make 4 bonds total. Right now, this carbon only has 1, so it needs to make 3 hydrogen bonds, right? So it's going to be a carbon CH3, okay? This one already has 2, carbon 2 has 2 bonds already, so it will make 2 more with hydrogen. Carbon 3 has 2 bonds already, it will make 2 more with hydrogen. There we go. 2 hydrogen bonds. Carbon 4 already has 3 bonds fulfilled. It has this guy, and this guy. Not to be confused with double bonds like these look like. These are all single bonds, but there are 3 of them. Okay, so 1, 2, 3. So it's only going to make 1 more bond with 1 hydrogen bond. Okay, and carbon 5 has 2 hydrogens. Carbon 6 has 2. Carbon 7 has 2. And carbon 8 has 3. 1, 2, 3. Excellent. So there is 4-ethyl octane. Oh, wait, I forgot to do the carbons on the ethyl group. Okay, this carbon on the first one is going to have 2 hydrogen bonds. And the carbon on the end will have 3. Yeah, it's messy and awful. And you may actually be able to write it smaller, writing on a piece of paper rather than a tablet. So hopefully you can. Next, we are going to draw the skeletal formula or the line angle formula. Okay, so easy peasy. We have 8 carbons. We do it the exact same way, but instead of writing carbons out, we draw lines. Okay, so I'm going to say I'm starting with 1 carbon and drawing a line. Now you have 2 carbons, 3 carbons, 4 carbons, 5 carbons, 6, 7, 8, right? Because every end of the line segment is a carbon, okay? So technically there's a carbon here, there's carbon here, there's carbon here, etc., etc. But we don't draw those because we're lazy and we're just trying to figure out how to draw this molecule. We're not trying to draw in every carbon because, there's carbons at the end of each one of these lines. Again, I keep drawing over these and making them look like double bonds, but they're all single bonds. All right, so excellent. We have 8 carbons going on. What else is happening? Again, at carbon 4, so I need to make sure I name them. 1, 2, 3, 4. I need to make sure I number them. 5, 6, 7, 8. Okay, at carbon 4, I have an ethyl group. That's 2 carbons. So I've got 1, 2 carbons hanging up there. That's all you have to do. Done. Skeletal model, done. And if you're fancy and savvy, you don't even have to write in the numbers. Okay, so you just say 1, 2, 3, 4, 5, 6, 7, 8. Carbon 4, 1, 2, 3, 4. Has an ethyl group, which is 1, 2 carbons. That is the official skeletal model for 4-ethyl octane. Much, much, much easier than the structural formula. Oh, goodness, yes. Okay, so what I want you to do is do number 2. So pause the video, do number 2, and then come back and check your answer. Okay, you ready to see your answer? Remember, you should have both the structural and the line diagram for 2-methylnonane. Hopefully the first thing you did was draw out your carbons. Nonane means 9. And so you draw 9 carbons, connect them up with their single bonds because we're still dealing in alkanes, which means they don't have any double bonds going on. And then if you want to, go ahead and draw in the rest of the bonds for each carbon. That makes it a lot easier to say, okay, I know each one of these has to be taken up by something. It's probably hydrogen, but maybe it's not. The next thing you did is you said, all right, what are my functional groups on nonane? There's only one, and it is 2-methyl. So on carbon 2, I draw in a methyl. Methyl means 1 carbon. And again, I said, oh, carbon needs 4 bonds. I'm going to draw the 4 lines. One of them is going to be bonded to that second carbon in my main chain. The rest, what are they filled with? Oh, they're going to have to be hydrogens. There was only one functional group. There's no double bonds. Nothing else is happening. So every other bond is going to be filled with hydrogen. And it should look like this. This is the structural formula for 2-methyl nonane. Now, next you had to do your line drawing. So first you hopefully drew your 9 carbons, like so. Then you're going to draw in your functional group. And you know your functional group is a methyl, which is only 1 carbon, and it comes off the second carbon in our chain. So your line drawing or skeletal drawing just looks like this. Depending on how you feel about the skeletal drawings, you might find them incredibly easy compared to the structural diagrams. You don't have to draw all those freaking hydrogens. It's so much easier. That's why organic chemists like to do this, because their brains are busy working out hydrolysis reactions and electrolysis, don't worry about it, we'll get to it, and all these other different chemical reactions. They don't have time to be drawing in these pain-in-the-butt hydrogens. So the correct answer for this problem, 2-methyl nonane, looks just like these two. Our 9-carbon chain with our methyl group hanging off, represented as both a structural and a line diagram. So you may be asking, well, wait, what if I drew my methyl group pointing up in the first one or pointing down in the second one? Am I right? Am I wrong? You are right for both of them. Remember, these, again, are 3D molecules. They can spin in space. So drawing them either way is equally accurate, because you could flip them, right? You even could have drawn it completely backwards so that this is carbon 2 instead of this one here. Again, it could flip in space that way. That's totally fine. As long as you have the methyl coming off of the second carbon in both of them, it doesn't matter which way it's pointing. Okay, let's look at this 3,3-dimethyl pentane. So we know the basics already, right? We're going to make that pentane chain first. Okay, so there's 5 carbons for pentane, right? And here's both the structural and the line diagram for that. So 5 carbons, awesome. Now we need to add our functional groups. Okay, so we've got, wait a minute, 3,3-dimethyl. What? Well, let's just break down what this means. Di means 2, and methyl means a 1-carbon chain. So there are 2 1-carbon chains, and where are they? They're both on the 3rd carbon. So we have a 3 here, or sorry, this is the 3rd carbon. No matter which way you count it, this is the 3rd carbon. So we have a methyl here, we have a methyl here. Yay, now we just have to add in our hydrogen. So that's for the structural one. If we go over here, here's our methyl, and that's done. The line diagram is done. However, the structural diagram still needs its hydrogens, okay? So instead of writing all of the bonds out, I'm just going to look and say every carbon on the end is going to have 3. So this is CH3, 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 CH3. Okay, fabulous. Every carbon inside we actually have to count and see how many bonds it already has. So both of the carbons next to the end chains, so carbons 2 and 4, already have 2 bonds, so they need 2 hydrogens. I'm just going to say carbon CH2, and this is kind of messy, so let me make it prettier. Come on, there we go. Okay, so this is going to be CH2. It's not letting me do the thing. Technology is being difficult. That's okay. So in this case, I will just draw my 2 hydrogens, hydrogen. If you left yourself more space, or if you can erase, you can just move the last carbon over a little bit, and then you can write the H2 right next to the carbon, just like we did on the H3s. Same thing over here. This will be an H2, okay? Fabulous. Does everybody have all the bonds that they need? Yes, they do. So both of our molecules are complete. So you'll see that 3,3-dimethyl, all it tells you is there are 2 methyls, okay, because it's dimethyl, and they're both on the 3rd carbon. Okay, so we didn't do this earlier when I was telling you how to be lazy about this, right? So and I say lazy, but it's more efficient. So the first way we named this was that we would have said this was 3-dimethyl pentane. Okay, that's fine. You can also say it is 3,3-dimethyl pentane, saying that there are 2 methyls, they're both on number 3. Fantastic. Hopefully that was easy to follow. So I'd like you to do number 3 as homework. Or sorry, no, I don't know if it's number 3. I'll do 3-ethyl pentane as homework, because that should be nice and straightforward. There's nothing strange about that. Also, this next one is homework. 3-ethyl 2-methyl heptane. That is also homework. Those are easy. Draw your backbones, your pentane and then your heptane backbones for each one, and then add your functional groups where appropriate. So let's look at this next one together. 2,2,3-trimethylbutane. What is happening? There's some crazy... Oh, wait, no. We're just going to start simply like we did before. If we're looking at a butane molecule, that means it has 4 carbons. 1, 2, 3, 4. That if we're doing our structural diagram, so this is the structural one. If we do our line diagram, it goes 1, 2, 3, 4 carbons. Excellent. And then we know there are 3 methyls in this, right? So awesome. There are 3 methyl groups somewhere on this chain. Where are they? There's one at 2, another at 2, and then one at 3. Okay, so for our line drawing, this is easy. We're going to say, okay, there's one at 2, and then another at 2, and then there's one at 3. Easy. For our structural diagram, there's one at 2, and then another at 3. Easy peasy, then just fill in your hydrogens. Okay, CH3. This one, the second carbon is completely saturated. It's not going to make any more bonds, so no hydrogens. This third carbon only has 3 bonds, so it'll make 1 hydrogen bond. All of these guys on the ends will have 3 hydrogens, and 3 hydrogens. So there is both the structural and the line diagram for 2,2,3-methyl-trimethylbutane. So notice how we just add that number prefix to the number of methanes we have that tells us, oh, we have 3 methyls and here's where they are. So that is a new wrinkle in this, but it should be pretty self-explanatory. So on the back or on the second page of this worksheet, I would like you to also do 3-ethyl 2,2-dimethylhexane for homework. Again, draw hexane, and then figure out where your functional groups are. There are 3. There's 1 ethyl and 2 methyls, so figure out where they are. And then, oh no, this one looks terrifying, but it's actually not once you break it down. So do the next one for homework also. So 2, 3, 4, 5, 6, 7 hexamethyl octane is hard to say, but is actually very easy to draw. You're going to end up with 6 methyl groups. It tells you exactly where to put them on your octane group. And that's all. Don't do any more on this page because some of them are repeats, and I actually found some errors in the rest. So that's it. Enjoy your weekend, and I hope you're feeling better. Bye.